Yeah, I
Okay,
do.
perfect. All right. So, thanks everyone for joining us today. I hope you all had a great week. So, today we have the pleasure to host Tianming Liu, who is a professor at the University of Georgia, and he'll share with us some thoughts on brain inspired foundation models. So, before handing the mic over to you, Tianming, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. In order to ask your question, you just have to type the word question or I have a question in the chat. And when the time is right, you can directly ask it. And of course, in order to ask your question, make sure to unmute yourself and mute yourself back when you're done. There'll be as also some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Tianming. That's pretty much it for me. So whenever you're ready, Tianming, floor is yours.
Yeah, sure. Thank you. So first of all, I'd like to thank Bon and Rim for the kind invitation and introduction. And it's really a great pleasure to be here and share my recent work and experience in brain-inspired foundation model. So this is really a combination of the topic in brain science and AI. The brain is extremely complex and very elegant designed intelligent system, and it has very complex and very efficient architecture, including the molecular architecture, structure architecture, connection architecture, and functional architecture. So my work in the past 16 years has been focused on discovering the brain architectures, including the building blocks, how these building blocks are connected and how they function together. In today's talk, I'm going to focus on three pieces first. So that is the structural connection patterns and structural architecture in the human brain. So the talk today, we are more focused on the macro scale architecture representation and learning and how we can use this representation to inspire and to capital design and implementation of artificial deep learning models. So in parallel, in the past 2.5 years, the foundation models have been the mainstream in AI field. Since the release of ChatGPT in late 2022, the large language models, multi-model foundation models have been playing a major role, and the pace of development of this technology has been extremely fast. If you look at the past 2 years, and we can see so many different models were released and developed and tested and applied in many, many different fields. And in the past 2 years, my group and my collaborators have been evaluating and using these most recent foundation models, including the most recent OpenAI 01 and 03, and which are very, very inspiring and very, very advanced for AI applications and run many different tasks. And in addition to this industry level, closed source and open source models, my group and my collaborators have been working on developing new foundation models for specific applications. For example, one for early work based on the prompt engineering, based on the fine-tuning of large language models, and further reinforcement learning of these large language models, and further to multi-model foundation models. So we can see in the past 2 years, we have been working very hard, and everybody's working hard to catch up with the very fast pace of foundation model development. And at the same time, it came to my attention and many other researchers' attention that the relationship between the human society and the human brains and the digital artificial general intelligence is a very, very challenging problem. So for example, we know that the AGI or artificial general intelligence is coming maybe in a few years, maybe this year, next year, so we don't know. But the bottom line is the super intelligent systems are already in place. For example, OpenAI 01 and 03 models, they are already very, very intelligent at the PhD level in many different areas. So a fundamental question for us to think about at this moment is how we are going to align those models, how to supervise those models, and even make them safe enough for human society. So one of my research agenda and vision is to develop digital human brains as the surrogate of human intelligence and human values, and interact with such AGI systems or the artificial superintelligence or ASI systems in the future, so that the human intelligence and the artificial intelligence can work together, can collaborate, and can inspire from each other. So that's the main topic of today. So, so to start with the theoretical foundations of this kind of vision, we know in the past decades, past dozens of years, we have making tremendous progress in the brain science and brain imaging and computational neuroscience. So with most recent imaging technology, we are able to reconstruct a biological neural networks at the very, very high resolution level, from all the way from synapse level to neuronal level, cellular level to system level, using human neural imaging. So at the same time, in the AI field, in the past decade, 20 years, the AI field has made tremendous progress in terms of designing artificial neural networks. And one of the main goals of AI or deep learning is to try to mimic biological neurons and biological networks and implement that in computation framework. So I think the theoretical foundation for brain-inspired AI is that eventually we will be able to model the biological systems, biological neurons, and the networks in the brains, and use those principles to inspire and to optimize AI systems, particularly with deep learning. So that is a theoretical foundation. So start with a very concrete example. About 2 years ago, my group and our collaborators have been working on the relation graph of vision transformer. So this idea was proposed in 2022 by Stanford group. They developed the relation graphs on top of a computation graph, which is the basic framework for most computational deep learning models. And the ideas on top of the computation graph, we built they call the relation graph to model the message exchange between the node in the deep learning models, and we use a vision transformer as one example, because this is a very powerful in the field of AI models, particularly with transformer. So, if you look at the evolution of many different VITs, the major advancement, the technology advancement in VIT is the better design of the message exchange patterns, all the way from the vanilla to original regular grid of node message exchange to more and more efficient message exchange or information exchange patterns or ways, so that the model becomes better and better. So based on this kind of inspiration, we construct a relation graph, which is kind of another abstraction layer on top of computational graph to model the message exchange in vision transformers. And then we compare this VIT-based relation graphs with brain graphs. Brain graphs meaning we construct biological neural networks all the way from worms, like from very small, very tiny animal brains, to rat, to cat, to macaque, and to all the way to human brains. And then we can look at the computational representation in both brain and the VIT graph, which means the relation graph. And the take-home message, the conclusion is that the more advanced VIT graphs or relation graphs, more close to the human brain graph and the brain graphs, they are more efficient, they're better. So that means if we want to design a good deep learning model using and modeled by relation graphs, they needed to be as close as to brain graphs as possible. So that's the take-home message. So that's another theoretical foundation for us to move forward. We want to design deep learning models, AI systems, including large language model. We can talk about that later. And their relation graph, their computational representation should be close to the brain as much as we can. So that means we can use the brain as the optimization target when we design and we optimize these computational models in the deep learning or in AI or any foundation models. So let's start with a very concrete example. The human brain, the mammal brain, is a very convoluted structure, and it's after millions and millions of years of evolution from all the way from rat to cat to chimpanzee to monkey to human brain. And this is the defining characteristic or feature of the human brain. So very convoluted folding pattern. And we can look at the folding pattern in many different scales, from the very local scale, for example, curvature, and then all the way to the human, the whole entire brain, including both hemispheres, all kind of gyrus patterns together. So this is extremely complex. My work in the past 10 years, 15 years has been develop neural descriptors or modeling tools to represent this very complex folding pattern. Then we'll be able to reconstruct such graph models from the human brain. And today I'm going to focus on the simplest folding pattern in the human brain and the mammal brain. That is called the gyrus and the sulcus. You can see here on the top is the gyrus, which is outward structure of the brain, and at the bottom is the sulcus, which is the inward structure of the brain. So any primate brain, including monkey, Japanese human brain, is always composed of gyrus and sulcus, of gyrus or sulci. So this is two types of basic unit folding pattern in the brain. And there are many theories, dozens of theories of why the brain is folded in this way, and we want to understand why it's folded in this way and how it is linked to computation in the brain and the computation models to inspire the AI. So here I focus on two series. The first series was published in 1997 in Nature by a group in WashU, and the series that called axon pooling theory. That means the axons between the gyrus wall that pull each other, and so we can have a gyrus like this. And about 15 years ago, my group developed a different theory, in the opposite direction. Instead of looking at the pooling, axon pooling patterns, we look at the axon connection patterns, and we found that most of the axons are concentrating on the gyrus. So we came up with the axon pushing theory. So the idea is that if you look at the structural MR and the diffusion tensor MR data, the human brain, and we can have the beautiful gyrus folding pattern. And if we visualize the endpoint of those axons and correlate them together in the same space, this is extremely important. Look at them in the same space, we can see that most of the axon endpoint follow the beautiful gyrus folding pattern. That means most of the gyrus are connected very dense axon connections. And if you look at the sulcus, which is at the bottom of the gyrus, and we can see that if you look at the gyrus fundi, which are represented by the tubes, we can see that most of the axons are patterned around this sulcus fundi. So that means much less connections or axon connections are connected to this sulcus instead of cordon around the sulcus. So we came up with a couple of quantitative studies, and we can see that the axon densities are much higher in the gyrus, but much lower at the sulcus. And we studied this kind of pattern in different brains using different primate model. For example, this is the monkey brain, and this is monkey brain, and this is chimpanzee brain. We can see the same pattern. Most of our axon connections are concentrated on the gyrus. And we look at the fetus brain, and that means the brain is still in the fetus stage, like from the 4 months to 6 months. And we look at the folding pattern, and we can see most axons are concentrated on gyrus pattern. So that means we can see much more connections in the gyrus and much less on the sulcus. This is another visualization of axons causing around the sulcus. So we also verified this result using histology data in the dog brain. So we did a neuron and axon staining studies. We can see that most of the axons are connecting to the gyrus and causing around the sulcus. So this is the first time we replicate this microscale neural human imaging in histology in dog brains. And we further look at the developmental stages of the human brain all the way from 0 year, that means the brain is just born, to 1 year to 2 years. We can see a lot of axons are concentrated on gyrus and 3-hinge gyri, and they become thicker and thicker, stronger and stronger. So that means it's very likely those axons are pushing the growth of the human cerebral cortex and morph it and fold itself into the gyrus and the sulcus. And at the same time, we also look at the mammals of the brain, look at the called ISH data, which is the transcription pattern of these 2,000 genes expressed in the marmoset brain. And our conclusion is that if you look at the gyri and salsa expression pattern, we can see a lot of exon attraction genes expressed on the top of the gyri, and a lot of exon pushing genes are expressed at the bottom of the salsa. So that means from the molecular perspective, the brain is structured in this way. So that means the axons are moving connecting the gyrus because morphogenes expressed on the gyri and other type of pushing morphogenes expressed on the salsa. So we can have this kind of molecular and the structure and the folding pattern in the human brain. So after all these studies in the brain structure, so what's the consequence? What is the implication in the functional architecture brain, and what is the relation to the AI? So here we propose another theory which is called functional architecture based on the bisectionally separated gyri and salsa, or series that on top of the gyri, they are the function hubs for global and the basic functions in the human brain. And at the bottom socket, there's a higher order local processing unit in the brain function. So you can consider human brain as a kind of system very similar to our transportation systems. For example, the gyrus of the big airport like Atlanta, New York, Toronto, and these are the local areas like Athens, Walkinsville, Lawrenceville. So if you want to go from one brain region, the gyrus, to another brain region in the human brain, you have to go through the gyrus and go through the very long distance axon connections in connecting those gyrus and then communicate with other regions. So this is a brand new brain theory, and we have already verified this theory in a series of studies using both functional MRI. We can see that the frequency in the gyri are relatively lower and the frequency in the salsa are relatively high. So that means the brain is segregated into two fundamentally different units, that is the gyri and the salsa. So that is the brain science part from the molecular structure and functional architecture perspective. So based on this theory, we developed called the core peripheral functional brain network architecture representation from the brains. And we use this architecture, the core peripheral principle, to inspire the redesign of transformers. So this is the computational model of the core peripheral brain network based on the previous study which I just talked about. So it turns out that the brain gyrus are the core nodes or core networks in the whole functional and cognitive architecture in brain, and those sockets are the peripheral node. And this model, this computation model, follow a core peripheral network or graph pattern, so that we can represent and get the parameter of this graph in the human brain, and then we can use this graph to have the design and redesign of region transformers. So that is the next piece of work I'm going to talk about. So on the top left is the biological brain network we just talked about, and the graph model of core peripheral models. And then because of this graph model is so efficient in the human brain, then we thought about why not use this model to guide the redesign of region transformers. So the idea is to let's reorganize the self-attention layers in the region transformer. So that means we reorganize the nodes that are traditionally equally weighted in the region transformer into two groups. One group is core node, another group is peripheral node, so that we can reconstruct the region transformer and reorganize the nodes across all these layers of self-attention layers in VIT. And so here is the mathematical description of this model. It's very straightforward, so we just reorganize it into two groups. And it turns out this is a really good direction to go. So for example, if we parameterize the optimization to two space using two key parameters, we can see a lot of sweet spot. In those sweet spots, if we design the region transformer following the distribution of this pattern, for example, the ratio between the core and the peripheral node, we can see those nodes represent a better or optimal or suboptimal parameterization of region transformers. They not only reduce the parameters in the region transformer, they also improve the downstream task of region transformer model, for example, the image classification, which is very classic traditional task, and we can improve this kind of image classification with a certain margin and also reduce the parameter size. And more importantly, we can see if we reorganize such a region transformer nodes, we can reorganize the attention maps, of course, and also we can move those key nodes or core nodes into more salient regions in the images, for example, in natural images and also in medical images. If we look at the medical image on the top bottom here, so we can see those core nodes move to the pathology areas in the mammograms. So that means if we optimize the nodes in the VIT using our corpus referral model, we can better extract, better explain those core nodes features in the image space, both natural image and the medical image. So this is a very experiment showing that if we do if we design the VIT in a way that is similar to human brain, like a corpus referral node, we can really save the space, save the parameters, do better classification downstream tasks, and also have a better visualization, better representation, and explanation of those models, those model key nodes. So we achieve these three benefits and advantage at the same time by just enforcing the brain-inspired model into the redesign of a region transformer. So any questions so far? Before I move forward.
Yeah, I have a question. How do you get those core patches?
Oh, right. So the core patches are automatically grouped because we started with the traditional region transformer. When we reinforce this kind of corporate distribution, some of the important nodes with larger and stronger connections to other nodes will automatically form at core node. So this is a learning process.
So you look at the attention map of the pre-trained VIT?
Right, that's right. We reorganize, we distribute the attentions. Yeah.
Okay, thanks.
And a little bit, if you can explain more about how you do this redesigning, grouping them into two categories, because I wonder how it's not simply a result of modulation of attention.
Right. So yeah. So here is the method we did the reorganization. So this we started with the traditional VIT, whatever VIT, your favorite VIT you can consider, and then because we enforce the corpus referral graph, if you look at the bottleneck pattern, we kind of iterate this kind of process and enforce kind of this. You can consider this kind of corpus referral loss to optimize this model. So eventually those models, those nodes we are grouped into two categories, either core or peripheral. Because most of the connections are very sparse, and the more dense connections with those nodes we have big groups to core nodes, others we go to peripheral. So yeah. It's a stronger constraint than the sparsity constraint.
But do you learn this strong constraint?
Yes, we learned this.
And you start from a pre-trained VIT that has been trained with regular self-attention?
That's right. That's right, yeah.
So is there like sparse connection being updated during the training process, or it is like?
Yes, of course. Yes, of course. Yes.
Okay, so
it's
the structure becomes sparse. Will it cause the differential problem? So whether it can be differentiated?
So in addition to sparsity, so we also enforce the corpus referral graph model. So yeah, so like this model. We have those parameters because we learn those parameters from the brain, and so we just want to enforce. So keep updating both the node distribution and the connection patterns all the way until to follow this kind of corpus referral pattern.
Okay, that's very interesting. Thank you.
Thank you. Okay, so so this really inspired us to even move forward. So in addition to redesign of this VIT, we also adopt this general approach to VIT domain adaptation. You know, VIT domain adaptation is a big problem. Whenever you train a model in on a specific data, the domain shift problem may cause some problem, the generalization problems in different data sets. This is particularly important in medical imaging. For example, you train a VIT or fine-tune a VIT model in hospital A, it's very likely the model won't be work very well in hospital B because of domain adaptation problems. So, inspired by the brain inspired or cooperative or redesign VIT, we adopt this idea into VIT domain adaptation. The idea is here. So instead of put those nodes in the equal importance, so we consider those core nodes as they call the domain adaptation core nodes. So when we do the domain adaptation from one VIT to another, those core nodes won't be changed. So that means that we keep those core nodes, because the basic assumption is that those core nodes will play a major role when you do the domain adaptation, and those core nodes should not change too much when you go from dataset A to dataset B. So this is a simple idea, works very well. After we tested this idea in different data set and compared with the state-of-art VIT domain adaptation approach, we have quite a good marginal improvement because we just fix the core node. We only do the adaptation in the peripheral node. So it worked very well. And also this improvement is enhanced by the visualizations of those core patterns and features. You can imagine those core nodes represent key features and that are more transferable and more generalizable across different domains. So that's how we can achieve such a good margin of improvement. So in addition to VIT, we also extend this idea to foundation models. So we started with the very traditional foundation model, multimodal like CLIP. The contrast reduction language imaging pre-training. This is one of the most commonly used foundation model in the domain. So the idea is, so instead of using the traditional CLIP, which is the if you look at the CLIP model, it's kind of a text encoder, text token compared with the imaging patch, and you kind of maximize the similarity using contrast learning. So that's the CLIP. Instead of doing that, we add a core peripheral network between the text layer and the imaging layer. So idea is, if we look at the text layer and image, we consider they should be classified or categorized in the both core node and the peripheral node. So that's the basic assumption. So it makes sense because if you look at the core node in the text, they very likely correspond to core node in the imaging domain. So that's how we make this assumption and add a middle layer called the cooperative network to match the core node. We redistribute the core node in text layer and also the image encoder. So that's the idea. And we enforce this core peripheral node to follow a graph pattern, which is parameterized by the brain model. So that's a very straightforward idea, but it works very well. For example, if you look at the test result, this core peripheral guided CLIP achieve a much better performance than traditional CLIP across all the MET CLIP. So that means, so the text encoder or text data and imaging data, they also follow a core peripheral distribution in their own domain, and those core nodes should correspond to each other in both multiple domains. And that assumption really works, and this is quite promising. So we keep going to look at.
Yeah. I have a question. Sure. For the CLIP setup, do you assume that there's an identical number of core nodes for both modalities?
That's right. We assume core nodes for both modalities, exactly right. And those core nodes should correspond to each other. They should be matched in the.
Like in most image text datasets, it appears that there's actually like less number of entities that are mentioned in the text than in the image. So how do you deal with that?
So yes, there's balance. So we test this in the medical domain. So in this called the chest expert data set. So we have both the imaging data the patches and also the text description. That's a radiology report. And then we also have the called eye tracking data, the gaze. So when the radiologists read the images, the gaze focus on the pathology patches, and then when they describe the problem, those patches in the text domain also match this pathology. So we use data. We just published a paper in last year's NIPS in Vancouver, and we have a very detailed description of those data sets, how we can match those text node to the imaging node. So, and we use the same data like here, because this work was a little bit earlier than the NIPS paper last year. So the basic idea is we do have such a pad text and images, and they are in good balance because we have thousands of such pads, and we did a fine-tuning on the clip model, so we keep that that balance actually. So in the medical domain, of course, if we go to general imaging domain like images and text on the internet, they could be such a serious problem, just as you just mentioned. But in the medical imaging domain, we already control that problems, and we make sure they're already balanced. That we have ground truth, because those pathology patches and images have to correspond to those patches and node in the text, because the radiologists read the images and say those texts at the same time but linked by the eye tracking data. So
okay, thanks.
Yeah. Sorry, I did not include that paper here, but so the idea is very similar. So by looking at the cooperative node in both text and imaging domain and then match them together. So, and after the visualization of these images and text, and it's really interesting that the optimized node in the images moved to the true pathology images. That's really inspiring compared to original clip. You can imagine original clip was trained on internet scale data, like images and text descriptions. They have no idea of the medical imaging pathologies. So it makes sense the clip, the hitbox does not conform to the pathology at all, because there's no medical information in those clips. There are some correlations between text patches and nodes and images, but not to pathology. So after fine-tuning, after using our cooperative node, you can really move those key nodes to the pathological regions. So that means the clip, the CP-based clip really help the medical domain at this. In this example, we do use both the cardiogram and also the breast cancer images, mammogram. We see the similar phenomenon. So that means the CP cooperative constraint really helps us improve the model performance, improve the interpretability, explainability, and the representation of the core features. So that's really inspiring. For the rest of my talk, I will move slightly from structured brain architecture to function. So function means we look at the fMRI of the brain function and also use that function architecture to inspire foundation models in terms of the function organization of foundation models and function organization of the brain. Okay, so the fundamental question is how we're going to represent human brain function. So this is a kind of fundamental question for the brain science for dozens of years, and my group has been working on this problem for over 15 years already. So we have called a Hockney theory. So the theory of our lab is that the human brain has like 400 basic networks. So these basic networks are the building blocks of the brain function. So you can see any brain function is a combination or composition of these 400 basic brain functions. And the difference of the human brain function is represented by or embodied by the different overlap or interaction patterns of these 400 networks. So that's our theory. So we have been working on this brain theory for 15 years, many publications. So that is core idea and take-home message. So any brain function, what you think, what you imagine, what you are planning, many different brain functions are just a different combination or different weighted addition or summation of those 400 basic brain networks. So that's, and we already have such 400 representations of those brain networks. So that's the basic theory. And then in addition to resonant state and task with fMRI, we use a relatively new or relatively different fMRI pattern that is called natural stimulus. So idea here is that instead of looking at the brain, doing very simple tasks, we stimulate the human brain by visual tasks. For example, let the human brain watch videos, listen to music, read stories, all kinds of natural tasks, so that we can watch your human brain in a naturalistic environment and understand how the brain functions in such natural stimulus environment. So this is kind of new paradigm, relatively new paradigm. And so we started with some exploratory studies 2 or 3 years ago. The idea is here. So because 3 years ago, we don't have much knowledge about foundation model. So at that time, we used a very traditional CNN model, which is ResNet. So here is the experiment we did. We show the same video. We show the same video data to the human brain, and we can watch the human brain by fMRI. We can have the whole brain recording of the brain activities. And at the same time, we show the same video to ResNet and see how the neurons in ResNet in CNN models activate, and how this activation along the time series are correlated with the human brain response. So that's what we call coupling biological and artificial neural networks. And the biological neural networks are the human brain imaging by fMRI, and the artificial neural networks are the ResNet 3 years ago. We have not worked on transform yet. So we then couple the activation patterns. It's very inspiring that if you look at the visual stimulus, because we can extract all kinds of filters and active images in the ResNet, and then we can go back to the original image after we have the activation patterns. If you look at the patches, many different types of patches. For example, here is the patches for like a bus. So if you see buses in the video stream, you can extract that patch. And those patches, when you see such patterns, have very consistent brain network, which is responding to these patches in our buses. So we can consider this function brain network as a bus understanding of bus response. And we can look at other, like a grid. If we, on the right corner, if you see all kind of grid patterns in the image or in the video stream, you can see another brain network is responding to this grid. And they have quite a high correlation, for example, 0.299, almost 0.3 Pearson correlation. So that means this network is taking care of the understanding and processing of this grid pattern, bar pattern, rock. You see rock, we can have another brain network. So you can see unlimited, so many different visual patterns in the video stream, and those stream response in the ResNet are very similar to the human brain's response imaged by fMRI. So there is a one-to-one correspondence in the human brain and the ResNet, doing the understanding of the same region visual stimulus, either in images or videos. So that's very inspiring. And then we keep going. We look at the brain's response to also the video, the audio. So we have audio that is a storytelling audio. So that means there's a language transcript. And then about 3 years ago, this paper was published in 2003, but the work was done in 2022. At that time, we do not have access to large foundation model, large language model yet. So we use a BERT, which is a very classic transformer of language model. And we show the same language script, the BERT model, and look at the neural activations in this BERT and correlate that and synchronize that with the brain response imaged by fMRI. So remember, we are showing the same story, same transcript to both BERT model and human brain. And then we find the synchronized, very synchronized activation patterns, and they're very reproducible. For example, we show similar semantic sentences in both two stories. One is Kapama, another is shape. We can achieve very similar activation pattern in the brain and similar activation patterns in the BERT. So we can couple them, and we can implement the semantic space represented by BERT and another semantic space represented by human brain, imaged by function map. So this is very inspiring. And further, in another work, so we look at the multimodality foundation model because in this work was done 1.5 years ago. So we look at a multimodal foundation model. We use the meter, which is very similar model to LEAF. So in this multimodal foundation model, we can look at the imaging to imaging, imaging to text, text to text, and text to image response in the multimodality foundation model, which is also a transformer. Look at the activation patterns in these 4 types of categories and correlate those patterns with the human brain. And here, instead of showing the brain and the foundation model in videos, we show that have 5,000 images. So that means we show the same image and text pairs to foundation model and the human brain. And look at the brain's response, the visual response, and the linguistic and language response. And it's very inspiring that no matter what format, either the visual or language or linguistic, they can stimulate or activate this very similar brain regions in two types of input or stimulus. And then we can see also the activations in the language models at the multimodal language model. So in this way, we can really morph the semantic space in the human brain and also the multimodal foundation models and look at all kinds of stimulations or activations in both brain and those foundation models, or use just one simple stimulus in visual or language domain. So this is a good example for us to understand how the brain understands multimodality and how the multimodal foundation models understand both language and text together. So, and we see very consistent patterns using both fMRI and foundation models. So another way to even move forward is we were inspired to design a brain-like organization, to look into brain-like organization like language model. So because the large language model like Llama 2, Llama 3, Llama 3.1, Llama 3.2, it's already multimodality. Those large language models, they can see, they can hear, they can listen, they can do language generation, they have even emotion patterns. So a fundamental question for us to look into is, do we see brain-like organization or functional networks in the large language models? So this is a fundamental question for us to move forward when we have AGI systems, ASIC systems. Do they even have consciousness in the large language models? So to really answer this type of question, we advance our previous study further to look at the brain response and the large language model response by coupling them together. The idea is very similar. So we show the video streams of both brain, which we can imagine them at the activity by fMRI. Also, we show the same videos to Llama 3, Llama 3.1, 3.2, and look at activation patterns in these large language models or multimodal large language models and map the activation patterns and correlate that to the human brain. So what we did is here, we used the called brain activation functions in the artificial neural network, that is Llama, and use that addiction learning and sparse coding to learn the basic unit, the basic pattern in the response, and use that as a seed dictionary to reconstruct the human brain function networks. So we use kind of supervised addiction learning learned from the foundation models and use that to reconstruct the brain's reconstruction of the brain activations. So it's very interesting that we can see brain-like organizations in the large language models, that is Llama 2.3.2 and 3.1. And it's really even more inspiring that if you look at the advancement of large language model all the way from birth to Llama 1 was released in early 2023, and then to Llama 2 and then Llama 3, 3.1, 3.2, we can see the more advanced large language model, they have more brain-like organizations. That means they are more and more behaving like the human brain. So that means we already see human brain-like organization or function networks in the large language models, the more and more closer brain. So that's really inspiring to us, because we can see when we train, we fine-tune, we do better training of large language models, we are training artificial neural networks that more and more look like the human brain. That's reflect what we talked about in the right beginning. We can use the human brain as the target of the optimization for alignment, for optimization, you name it. So we can use it further. We can use it in reinforcement learning to really align the large language models, foundation models towards the human brain, so that in the future we can represent the human brain value, human brain intelligence, human brain memory, human brain behaviors in large foundation models. So I think that's the very promising direction we are heading towards. And even further, we are trying to build a digital brain from the fMRI data. So here is what we did. It's called BDI, brain dialogue interface. So what we did is just design called a BDI model to represent the human brain function. So we use the click, the very traditional click model, to encode the text, encode the image. We can Google any internet image from the website and use that image to be encoded by CLIP, and we use that as a called a spatial query layer to fine-tune our model. So basically, we build a brain model, a digital brain model that can generate the human brain's response by any input, natural input like text or image. And what we did is just design a foundation model using fMRI data. So we used any voxel or location in the human brain and use the fMRI data to represent brain function and design very similar transformer structure. For example, we embedding all the vector voxels, and we have functional, we have the max fluctuation. We also encode all the positioning encoding, temporary encoding in the transformer. So basically, we design a foundation model for the human brain function. And then once we have the brain function foundation model, we can encode and decode from the natural stimulus. For example, here I show you the natural images Googled from internet. We can use this as input and predict the human brain's response based on our BDI brain foundation model. And here's another example by using text. For example, using text, put any language text to the brain, and we can predict your brain's response using our brain's foundation model. And turns out that the output of the prediction, which is the red and the ground truth of our brain's response, because we can use the fMRI as a ground truth, and it turns out that they look quite similar. So that means we are already towards building a foundation model for human brain to represent brain function and use that to encode and decode electrical stimulus, include both image and text. So here's the region that we are working towards. So on the left, you can see the human brain, which is very complex, enormous complex organ that represent all human functions. So after dozens of years of brain research, we already know so many details of brain function. For example, the fMRI study, the fold independent study I just talked about in the past half an hour. So we will be able to build a foundation model for the human brain that's on the left, and we know all these function networks and the function representations. We have like 100,000 fMRI open data sets on the internet. We have enough data sets to model this human brain function. And on the right, you can see this is a foundation model. You can name or AGI, whatever you call it, AGI, ASR. So it's coming in a couple of years, maybe this year, maybe next year. So they already have very, very advanced functions, including perception, including reasoning. That is very important. Capability of AGI system, reasoning, have emotion, all kind of advanced functions in the AGI systems. And we want to align both the AGI and multimodal foundation model towards the human brain. And at the same time, we can use in the brain model, we just discussed a lot about the folding pattern, the function architecture, to inspire, to supervise, to align such AGI systems and multimodal foundation model. And in the future, I hope we can have the both human brain and AGI systems can communicate, they can talk with each other, they can even collaborate, and they can inspire each other, and they're working together, and they can be aligned to each other. For example, align the AGI system, human brain, and hopefully after this, all kind of things are accomplished, we hope we will be able to build a digital human brain, or we can call it a digital queen of the human brain, and those digital queens of human brain are represented currently represented by AGI-CSS, like large language model, large foundation models in the future. They can represent our value, represent our intelligence, even represent our memory, and so they can do things for us. And we can use the human brain as a kind of a supervision system to align those AGI system. For example, if the AGI system they have malicious attention, we can immediately detect such a malicious attention and stop it. So this is also extremely important for the safety of AGI and ASS systems in the near future. So that's kind of the big picture. So we are working towards in addition to this brain and AGI morphing or fusion study, we also look at how we can use the digital human brain to understand neurological disorders, including autism, including Parkinson's disease, Alzheimer's disease, MTBI, PAE, you name it. So the basic idea is that we already have the digital model human brain because they are already aligned to human brain, and we can dissect, we can watch, we can analyze, we can model each individual neuron's response. And we can understand the basic mechanism in the artificial neural networks. And we can also use this as a model to understand brain disease. For example, what happens if we can, say, train a depressed large language model? We can modulate, we can fine-tune it, we can align such models, understand how the mental disorders like depression works. And we can also answer fundamental brain science question, how the brain is trained, how the brain is learning by fine-tuning those parameters across those neuron connections, and what is the really true intrinsic mechanism of learning and memory. We can use the large language model, foundation models to understand that. We can even have some traumatic or physical damage to those neurons in the digital atlas. Say we can physically damage some connections, physical damage some neurons, and maybe those neurons are related to some brain function, like emotion, like a bipolar disorder, like Alzheimer's disease, like autism. So this opens up a whole new world of using large language models, study brain science questions of study brain disease. So, and in the future, I hope we can have like digital human brain model of brain disease. 600 major brain disease, all the way from Alzheimer's disease to autism to Parkinson to a traumatic brain injury. So that will be brand new research area for brain disorder research. So I think that's the end of my talk, and I will stop here and hope we have some time to answer your questions if you have. So that's it.
Yes, thank you, Xianming. I'm doing the clapping for everyone. So we have a few minutes if there are some questions. Feel free to directly ask it if you have one.
Thank you, Professor Liu. The talk is very interesting and inspiring. And so I saw you have compared several different aspects between the human brain and the digital brain. Right. So one very interesting problem I want to ask is that, so people know that the energy efficiency of human brain and LMs are quite different, right? So do you think, is it the reason, is it because like the topological structure of human brain is fundamentally different from LM structure, or is it because the difference of the just biological materials and hardware implementation and so on?
Yeah, great question, Bon. I think I would say I would answer your question from two perspectives. One perspective is as you just mentioned, the human brain has 100 billion neurons, 100 trillion connections, but it's only 20 watts, extremely energy efficient. But if you look at the artificial neural networks, the implementation is a big problem. For example, any computation neurons, no matter what activation pattern, activation function you have to implement your computation neuron all the way from NVIDIA GPUs to CUDA libraries, to TensorFlow libraries, to Keras libraries. So there's so many intermediate layers to maintain the status of a simple computation neuron, either it's 1 or either it's 0. So this is extremely energy inefficient. So I think the real solution to this energy efficient problem is neuromorphic computing, which is another new area I have been working on for 2 years. The neuromorphic computing is kind of to mimic neurons and the synaptic connections using physics neurons. So instead of using the computation neurons, so ideas they have spiking neural networks. If the neuron spikes, you have one, you send out the message. If the neuron is silent, you don't do anything, you just keep silent, you do not consume any energy, because in many cases, the neuron activation is so sparse. Only very few neurons are activated. But unfortunately, if you implement these neurons by deep learning at this moment using GPUs, you have to keep the 0 and 1s at the same time. Even though the neurons are not firing, not finding anything, you still need to consume energy to represent such zeros. So that is a fundamental problem. But if you use neural model computing, if you only spike, using spike neural networks, you save a lot of energy, right? So I think that's a fundamental solution to this kind of energy efficient problem. Of course, if you optimize the graph models in the human brain and use those optimized graph models to guide your redesign of the different models, that also can help. As I mentioned in my first part of the talk, you can use the more optimized graph models like cooperative models to really reduce many parameters that you really don't use, you don't need. So that's called capacity cooperative constraint. So I think we can do both, but optimize the model itself and implement it in a much better way. For example, using neuromorphic computing, I believe.
Thank you very much. Yeah, that's very inspiring. And I have long been interested in the spiking neural, how it works. So
right.
One question about this is that, so usually for LMs, now the scale is spanning from, let's say, typical 7 billion to more than 500 or even 1,000 billion scale. And
right.
for human brain neurons, so if I remember correctly, it's also about a few 100 billion. But
right.
research which shows that each single biological neuron actually is much more complex than a single artificial neuron. So if we do an equivalent comparison, how large is the scale, or how complexity, the complexity of biological neuron is approximately about how large of the, let's say, LM models, because they're not comparable for each one single biological neuron to one single artificial neuron.
Right. I think if you look at the neuron scale, the singular cellular scale, current biological neurons is way more complex than our computation neurons, right? If you do any computational, we just simulate the activation function, activate and stimulate. So that's it. But it's already doing very fantastic job for us in terms of the deep learning. So that's why the pioneers like Jeff Hinton, they already invent all kind of backpropagation algorithms to implement these neurons. But in terms of the whole brain scale, I think a current model like a 4 or 5 billion model of Llama is already in a decent scale as the human brain, and do very good jobs in terms of reasoning, in terms of perception. But I think so it's all about the scaling now. I think a current large language model, we already pretty much at this scale. For example, if you look at the OpenAI's O1 model and the GPT 4.5 model, I think in terms of scale, in terms of number of neurons, the artificial neural network is already at the scale of human brain. I think what we really did is doing much better training, much better learning, inspired by the human brain. The human brain is still doing a much better job in terms of like creativity, like consciousness, all kind of high order functions. So I think a very interesting direction is how to represent human brain high order functions and implement these high order functions in large language models. So in this kind of scale and this kind of level, in addition to the number of neuron, number of connection scale, I think we already pretty much reached there already, I believe.
Thank you very much. That's very inspiring.
Sure.
Atta, feel free to ask a question.
Yes, thank you. I was wondering, what is this measure of time consistency that you have used to compare with Llama, different models of Llama, and why you didn't use this brain score and like this Pearson R correlation? And why do you think this is a good measure to say if this is brain-like or not brain-like? Because it's obviously a very heavy term to say.
Right. So the temporal resolution could be very different. For example, fMRI, you have like a 1 second or 2 second TR. For EEG, you have a millisecond. Of course, we can do both EEG, we can do fMRI, but we have to align them together, as you mentioned. So currently, we just use a very simple Pearson correlation. Of course, we can use the mutual information, many other metrics. But it turns out we tried them before, and it's very similar. No matter what metric you use, they look very similar. But the bottom line is we need to do resampling of those time series because they are in different scales. Maybe in the future we can do in both a combination of hybrid temperature scale. For example, we already have the simultaneous fMRI and the EEG scan of those video natural stimulus fMRI scans, so that we have millimeter and then millisecond and second scale, and we can look at the artificial neural networks response in this scale as well. So eventually we need to align them together and look at their both the similarity and also the difference of time series. And of course, in the future, we can have better foundation models for time series data, and then we can use those foundation models to do even better embedding of the time series and do better similarity metric. Of course, we can do that. Yeah. Does that answer the question?
I'm still not sure what is like time consistency and how do you like how Llama 3 is more brain-like than
Oh yeah.
yeah.
Oh yeah, so I skip some technical details, but our paper is online. If interested, we can go to my website and go to the brain-like organization of Llama. So a lot of technical details. We just submitted this to ISML. Yeah.
Thank you.
Sure.
Any other question?
Any other question?
All right, so then let's thank Qianming again.
Thank you.
Thank you. And I'll
Thanks.
end the recording.
Thanks. Bye.
Yep.